Good day, gentlemen. This video is going to be a review of problem 2 on the exam review. So let's go ahead and get started. So first, this problem has to deal with a structural member in tension. A free body diagram analysis of a simple bar subjected to a constant uniform axial deformation, basically tension, conveys that the average normal stress, units of pressure, at any point on the cross-sectional area is a function of the internal resultant normal force and the cross-sectional area of the bar. So first off, we're using dimensional reasoning to determine the form of the equation for the average normal stress. So what we're going to do is use this statement right here, that the average normal stress at any point on the cross-sectional area is a function of the internal resultant normal force and the cross-sectional area. Okay, so the average normal stress, sigma, Greek letter S, small s, big sigma, you'll probably recognize from math as that, big E, or sideways M or W. Okay, so stress is a function of the resultant normal force, F, and the cross-sectional area, A. Okay, so all dimensional analysis problems begin this way. Sigma equals a function of F, comma A. So our dependent variable is a function of our independent variables. So this is the functional relationship. Okay, next, after we've got the functional relationship, we write out our power law expression. So if this is true, then it must be true that sigma, well, it's very likely to be true, that sigma is equal to some constant times F raised to some power times A raised to another power. And this we call our power law expression. Okay? Alright, so now if this equation is ultimately going to be correct, that means it must be consistent. And if it's consistent, so we're looking for a correct equation. And if it's correct, it must be consistent. And if it's consistent, then the dimensions must balance. So what we're going to do is, to get to here, we're going to first make sure our dimensions balance. And then we'll get up to our correct equation. Almost our correct equation. We should say the form of the correct equation, because we won't know anything about this constant from dimensional analysis. Okay, so after we've got our power law expression, we say that if that equation is ultimately correct, then the dimensions must be consistent. So the dimensions of the left side equal dimensions of the right side. And here's where we can substitute the dimensions. So this means the dimensions, bracket, dimensions of stress equals the dimensions of the constant times the dimensions of force raised to some power times the dimensions of area raised to some power. So dimensions of stress, it says it's got pressure. Pressure is ml negative 1 t to the negative 2. Force is ml t to the negative 2. Area is L squared. And constant is just 1. So we go from here now, we substitute all of these guys into this equation, and we get ml negative 1 t to the negative 2 equals, dimensions of constant is 1, so then we get ml t to the negative 2 all raised to the a times L squared all raised to the b. So what I've done is we've substituted this into here, we substituted this into here, and we've substituted this into here. And this is what we end up with. So now we're just going to simplify. So I distribute the a, the exponent a, m to the a, l to the a, t to the negative 2a, times l to the 2b. We combine like terms, so we get m to the a, l to the a times l to the 2b is l to the a plus 2b. There's one of our first rules of exponents coming back, times t to the negative 2a. And this is simplified on the right side now, so I'm just going to pull down the left side, l to the negative 1, t to the negative 2, and I'm just going to put a 1 here. It's a given, but I'm just going to write it anyway. Okay, so this statement, if we look at m, means that a equals 1. That exponent must be equal to this exponent for our mass dimension to be consistent. Okay, and if we look at L, negative 1 equals a plus 2b. We know that a equals 1, so negative 1 equals 1 plus 2b. So we subtract 1 from both sides, we get negative 2 equals 2b. b therefore equals negative 1. And then we don't have to look at t because t is going to be negative 2 equals negative 2a. We already have a, but we could have solved it more simply here. Okay, so now if a equals 1, notice I'm not boxing a and I'm not boxing b because we only box our final answer. So here we've got a equals 1, b equals negative 1. So if we go back to our power law expression here and we substitute our a in and our b in, we get our answer to be sigma equals c times f to the first, a to the negative first. So sigma equals c f over a. Now, we can check our answer if we check the consistency of this equation. So stress we see up here is ml negative 1 t to the negative 2. Force is ml t to the negative 2 over L squared. When you simplify that, you do see that these two sides are consistent. So that means that this equation is consistent. And this is the answer we're looking for, hence the boxing. Okay, so part A says use dimensional reasoning to determine the form of the equation for the average normal stress. Average normal stress equals CF over A. It's the form of the equation because it's got a constant and not the actual constant of the equation in there. So let's go to number 2, part B. Alright, number 2, part B. Outline the scientific method using the stress in an axial loaded bar as an example. So using that problem above as an example. Hint, dimensional reasoning, experimentation, and data analysis should be included. So first, what we'll just do here is Google the scientific method. And we'll refer back to that in a minute. But let's see what we've got to do. We ask a question. Ask a question. Okay? That's first. Now, to outline, we're supposed to give a brief account. So when we ask a question, you should be a little bit more specific in your answer than this. So ask a question about some physical phenomenon. Okay, great. Second, after we ask a question, we form a hypothesis. Now, our hypothesis in this problem is that our equation is going to be this. This is our hypothesis. So our hypothesis is actually based on some kind of research. So sometimes we'll see hypothesis as our second step, sometimes we'll see research the situation. So analyze as much as possible. So we'll say analyze and research, look up information as much as possible. Next would be form a hypothesis based on the results of research. Makes sense, right? So we ask the question, so what is the normal stress going to be? Then we research, we take a look at the situation. We're told, typically we would guess, that stress is a function of force and area. And so we use that relationship, that research, to do dimensional analysis to get down to a hypothesis, an expectation for that relationship. And after we form a hypothesis based on the results of research, we design and complete an experiment. To test our hypothesis. And after we complete the experiment, we analyze data. Analyze data gathered. So again, I'm adding a few extra words because the command term outline is being used, which means give a brief account. So we analyze data gathered in the experiment. Next, we make some kind of conclusion regarding a hypothesis. So conclude on the validity of our hypothesis. And then last, we can answer our question. Using results. Alright, so now let's take a look at what Google says about the scientific method, Wikipedia in this case. Alright, so the scientific method. Blah, 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 blah. Blah, 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 blah. There we go. Formulate a question. Hypothesis. Prediction. So you're going to get it in different ways from different people. Test, experiment, analyze, and then we've got our conclusion. We just do a quick image search, pull up one of these nifty little graphics, ask a question, do background research, construct a hypothesis, test by doing an experiment, analyze, draw a conclusion, and report. In our case, we want to go back to the original question. We don't necessarily just stop at the hypothesis, we go to our original question. Okay. Part C. Use the given Excel spreadsheet of stress lab data to format the given tables so they look professional, plot all necessary graphs and format professionally. Okay, so let's start there. So what we've got here is our data. Okay, now, the issue with this data is it's in a single table. And what we've got is we've got our stress. So I'll go up and change the Greek. We've got our stress, sigma. We've got area and force. And both of these, so if we look down area changes at some point, a few times. Force changes a few times. So we've got all of our data in one single table. The problem with this, we could do a mathematical analysis of our data. It's just much simpler if we're only dealing with one independent variable. So we want to separate this out. So we've got, F and sigma with A constant, and then A and sigma with F constant. So let's go ahead and do that first. Actually, first let's go ahead and add some stuff in here. So we've got force. I'm just going to title this force. And then F is the variable that represents it, and then the units are going to be newtons. Area. We title it. We've got the variable A that represents it, and we've got the units, we'll say meters squared. Stress. We've got the variable sigma, and the units are going to be pascals. And it's still in Greek. Pascals. Alright, good, and then I can just center this stuff. So it looks a little bit better. I'm not going to put borders on the X, we're going to separate it. So basically, if we look at force, we've got 10s, 15s, 10s, 15s, 10s, 15s, 10s, 15s. So if we can keep all the 10s together, then where all the tens are, the tens will be constant, and then the area changes. So let's go ahead and highlight all of this. I'm going to sort. Sort is this button that looks like that, A to Z, sort smallest to largest. So we go ahead and do that, and then we've got all the tens together. See under force, and then all the 15s together. So what I'm going to do here is I'm just going to copy this over to here for a minute. Let's do it right there. And I can copy this. And so now what we see here is force is constant, area changes, stress changes. So now I'm just going to say, I'm going to delete this and say that force is constant. So our constant is force, and it is 15 newtons. Now, I like the way this looks, so I'm just going to slide this down here. I'm going to go ahead and rotate the text, or you can also right-click. Remember, you can always go to Format Cells and change it however you want. Alignment, face it upward. There's that. Now I'm just going to highlight all these and merge them. So that looks pretty. Shorten this back up. Alright, now we've got force as a constant here. Let's go ahead and put my border in. And area and stress change. So force is constant, so now I need a table where area is constant. So what I'm going to do is I'm going to highlight all this stuff and I'm going to sort it by area now. So what I can do is just right click, sort, custom sort, and I'm going to sort by column C. Now on the exam, I'm actually going to have these separated out for you by constants. So you don't have to worry about doing all this sorting that I'm doing right now. I'm only showing it in this video because it's useful and you guys will need it eventually. But on the exam, you will not have to sort the data like I have just done. So now the area is constant at 0.1 square meters. So I'm just going to put here constant is area 0.1 meters squared. Alright, so I'm going to rotate that text up, merge these cells, shrink this back down, center this, make it narrower, and there are my two tables. Alright, so here we've got force and stress, constant is area. Here we've got area and stress, constant is force. So I'm going to go ahead and make these bold. I think what I'm also going to do is just get rid of that middle border. Yeah, and then get rid of the bold here. Yeah, this looks better to me. Okay. And I'm going to move this down. So we can have one plot here and one plot down here. So what we want to do is plot log log. So here we'll have log of force. And here we'll have log of stress. So this cell, and down here we'll have log of area, and here we'll have log of stress again. Okay, let's merge these, make it look better. Alright, and then I can add some border. Okay, so this cell is going to equal the log parentheses of that. I'm using an Excel function. It's basically a built-in equation. I copy it down. Now what we got here is log of C4, log of C5, log of C6, log of C7. Here we've got log of E4, E5, E6, E7, and so on. So I can go ahead and paste this down here too, and paste it there, copy this down. And that's my data table. So now what I can do is plot. We've got dependent versus independent. So X values, log force, Y values, log stress. Insert, XY scatter. There it is. To format this professionally and get rid of the series, I go to Layout, Chart Title. Chart title for this one is going to be a log of stress versus log of force. And axes, x-axis, log of force, keep my capitalization constant here, and y-axis, log of stress. I get a trend line on here, display equation, y equals 1x plus 1. Okay, so the slope of this line is 1, which means the exponent of f in our equation must be 1. If we go back to our work, f to the first power. It's f to the first power. So data does corroborate that analysis. Now we can do, let's go ahead and take this data, log A, log S, insert, XY scatter, delete the series. It's linear, right click, add trend line, display equation, and we see that the slope of this line is a -1. So the exponent of A must be -1. And again, if we go back to here, A is a -1. Okay, great. So now we go to our file here, format the given tables so they look professional. I would say that these tables look professional. So check. Plot all necessary graphs and format professionally. So we've plotted the log-log plots, those are the only ones necessary. I've formatted this one, so it's professional. I have not formatted this one. So for full credit, I should put a title in here. I should label these axes. So I'm going to give a red on that one because I haven't done it. Corroborate the outcome of part A above. Describe the results in the analysis space below. So part 3. As the attached Excel data plots convey, the relationship between stress and force and the relationship between stress and area let's see, so the relationship between stress and force is linear, and the relationship between stress and area is to the -1st power. It's also linear with a decreasing slope. Alright, and you might want to say a couple other words about that. Determine the value of the constant. Okay, good. So this will be extra credit on the exam, but this is very easy. So if we go back here, here's our equation. Now, the constant. We want to use our data to find the constant. And the simplest way of doing this is just to solve for the constant algebraically. So here we've got sigma equals C times F over A. If I want to get C by itself, isolate the variable, I first have to multiply both sides by A, because that cancels this. And then I have to divide both sides by F, because that divides out this F. So I end up with C equals sigma times A over F. So if this is the case, if C equals sigma times A over F, I can take either of these two data tables. Let's go here. And I'm going to have a column in here for our constant, C. C equals A over F. So this cell is going to equal A. A in this case is 0.2. Is that right? 0.2 square meters? No, this is 0.1 square meter. So C equals A, which is 0.1, times, let's look back at this again. C equals sigma times A, which is 0.1, over F. So it equals A times sigma what's going on here? Sorry. So our constant C equals, go back to our equation, sigma times A over F. So this equals sigma stress times A, which is constant at 0.1, all over F, so divided by F. Copy that down. Constant is 1. Interesting. So let's go ahead and verify this down here. So again, C equals sigma times A over F. So in this case, if we have C here, constant C, C equals sigma, which is stress, times A, which is there, all divided by F. F in this case is constant at 15 newtons, so divided by 15. And again, our constant is 1. So, back here, determine the value of the constant in your answer, part A above. So IV, the constant as calculated in the attached spreadsheet is equal to 1. Okay, very good. So finally, what is the stress equation? So the stress equation is sigma equals C F over A. C we just calculated in Excel as 1, so sigma equals F over A.